Good morning, I'm Francesca Marcello and today I'm presenting a research work focused on smart building energy and comfort management based on sensor activity recognition and prediction. After a brief introduction about smart buildings and some of the key points that characterize them, there will be the explanation of the problem under investigation and the presentation of the system that here is proposed as a solution. In particular, there are three main elements of this system that will be explained in details, which are a module for the recognition of activity usually performed by users inside their home. The second is a module for the prediction of these activities once they are known by the system. And the last one is about the scheduling of the appliances of the home according to user habits. Then there will be the presentation of the simulation that were done and the presentation of the results obtained. And last, there are going to be the conclusions and the future works that are going to be addressed in future. Smart buildings are characterized by the presence of sensor, actuators, and smart devices that give the opportunity to building energy and comfort management systems of providing support to users of various intelligent buildings. In particular, these systems are focused on monitoring and controlling key equipment inside the buildings and understand the user behaviors with the aim of providing users with tools that support cost-effective solutions in appliance management. To develop such kind of system, it is necessary to monitor users' habits, learning their preferences and predicting their sequences of performed activities and appliance usage during the day. Most of the literature consider user comfort as a set of constraints on appliance usage, which are a priori set based on general statistics. Furthermore, most studies that are focused on activity recognition and prediction don't consider a complete system for smart building solutions. The main idea is then to realize a system that is continuously monitoring user preference and habits about appliance usage, thanks to a non-intrusive sensor network, so that it can automatically recognize the activity usually performed by users and predict future usage of appliances. In this way, the system can manage cost-saving appliance scheduling based on user preference and expected energy consumption. In this slide, an overview of the proposed system is presented and we can see the all different modules involved in the process. First of all, sensors are used to make observations on the users and on their interaction with the surrounding environment. The event detection module combines the observation into events with meaningful information about activities done by the users. The activity recognition module recognizes the activities thanks to the correlation between detected events and activities, while the user profile module stores all the habits given by the recognition of the activities. The information from user profile and recognition module are then used by the activity prediction module to predict the following activities that are expected to be carried out by the users. Next, the appliance scheduling module uses the information from all the other modules to find a scheduling for controllable appliances that can guarantee the best trade-off between energy cost reduction and user comfort. More in details, the activity recognition approach encompasses two phases that are the training phase and the running phase. During the training phase, the system learns the association between activities and sequences of detected events. For example, as we can see in the slide, let's suppose that we have a space of events consisting in only 3 events, and that we are considering 2 different activities, A1 and A2. Every time the activity A1 is performed, we have one different instance of that activity that depends on the sequence of detected events during the time window OA. We then obtain a feature vector for every instance that, for each event, take count of the time this specific event is observed with respect to the total number of events observed inside the window OA. Finally, we define a model vector for each activity, such that every feature corresponding to a specific event is the average rate for all the observed instances associated with the same activity. Instead, during the running phase, the observed events are divided into subsequences of predefined length equal to size w and starting and time at time t. The algorithm computes a feature vector with the rates of events occurrences. This vector is compared with a model vector obtained before from the training phase, and it is then classified based on its probability to belong to a given activity. The main task of the prediction module is to provide a possible scenario in time t ahead in the future. The algorithm evaluates all the probabilities of the activities to be performed next in the future thanks to the statistics information about all the other activities carried out and recognized before the current time. The probability of each activity is then translated into the probability of one of the appliances of the house to be used, and this output is then used by the next appliance scheduling module to make a coherent scheduling of the appliances and to make the evaluations about energy consumption. The last module is then the appliance scheduling module. This algorithm dynamically shifts the task of the controlled appliances to time when it is more convenient, like off-peak times. It evaluates the scheduling, finding the best trade-off between the overall energy cost and the annoyance experienced by the user due to this shift. In the table are shown different activities that can be performed by the user taken from a real-world dataset and the corresponding appliances that are used during these activities. Only 3 of the appliances among those present in the house are controlled for the scheduling, and they are the water heater, the washing machine, and the dishwasher. 4 different activities are linked to these appliances, and the scheduling algorithm performs the scheduling only when one or more of these activities have a value of probability to be performed that is higher than a certain threshold. All simulations were done using the same dataset, considering 6 weeks of training and 1 week of testing. The activity recognition algorithm has an overall accuracy of 82.3%, while the prediction algorithm gives an accuracy of 67%. For the evaluation of the scheduling algorithm, 3 different scenarios have been considered. The first one is the classic situation where appliances are normally used by the resident and the scheduling is never programmed. The second one is based on a perfect knowledge of the time in which the user wants to use some of the appliances in the house. This case can be the one in which the user instructs the system about the moment they want the appliances to start, but it has the disadvantage of requiring lots of interactions between the user and the system. The last one, instead, bases its scheduling evaluations on the probability of using any of the appliances at the time t, calculated as explained before for the prediction module. We've called this scenario the scheduling based on probability. In the table on the left are listed 2 different tariffs for energy pricing, with one that is more convenient during the off-peak times. while in the table on the right it is possible to see how the two systems with the scheduling affect energy consumption that can be a decrease of at least 39.2% in contrast to the case without scheduling. The graph in this slide shows the energy saving over the week, differentiated by the three appliances that we are taking into account, and considering both the scheduling based on probability and the scheduling based on the knowledge of the preferred time for the user. It is evident how most of the savings come from a wiser use of the water heater, thanks to the scheduling only at appropriate time, while there is a lower incidence from the washing machine and the dishwasher. This can be explained by the fact that the preferred times for the use of these appliances are already evaluated as the best compromise between energy consumption and user comfort. Especially because in most cases they are used in times very distant from the periods of non-peak hours. We also evaluated the annoyance caused to the users by the scheduling of the appliances. Values of annoyance go from 1 to 5, where 1 indicates that there is not any discomfort for the user in the change of the time in which the appliance was turned on, while 5 indicates the highest level of annoyance for the user. We have found that in most cases the level of annoyance was always very low. There is only one exception in the case where the scheduling is based on probability, where there is a higher level of annoyance in the use of the water heater, due to the fact that this activity is linked to this appliance is linked to two different activities. And one of these is the activity of washing the dishes, that is recognized and predicted with some problems because it is often confused with another activity that the user performs. So there are some errors in the prediction of this activity that led to a less accurate scheduling and to a rise in the level of annoyance. In conclusion, results obtained with the proposed system show that the appliance scheduling can guarantee energy saving and reduce consumption in comparison with a classic use of energy and appliances. The prediction module permitted a quite accurate scheduling, even for several hours ahead in the future, basing only on probabilities. Furthermore, it was possible to guarantee that the annoyance rate was never too high, thus respecting user comfort. Future works will focus on testing the adaptability of the system to different real-case scenarios and on improving the prediction algorithm. Also, it will be evaluated how the presence of renewable energy sources could affect appliance scheduling and improving energy savings. And finally, the system could be expanded considering information about users' health and finding a correlation between right or wrong habits and user psychophysical health. Thank you for your attention.